Remember that one of the skills we've learned in this series of videos is how to take overall vectors and break them into components. Well, now we've done that twice. We broke this overall vector of 6 into the two components, positive 5.6 and positive 2.1. And then we broke this 4-meter vector into components, positive 3.6 and negative 1.7. So I hope that you're feeling much more comfortable now with that skill of breaking overall vectors into components. How do we break vectors into components? Well, we find the adjacent side by multiplying the hypotenuse times the cosine. And we find the opposite side by multiplying the hypotenuse times the sine. I hope you're getting pretty comfortable with these two ways of finding the components. Remember again, the trig functions only give you magnitudes. You have to figure out the signs on your own, but the signs are just as important as those magnitudes. I might mention, maybe for the last time, something I've emphasized a lot in these videos is a lot of people assume mistakenly that the cosine always gives you the horizontal component. A lot of people tend to assume that the cosine gives you the horizontal x component. That's not always true. Here was a case where the cosine was giving us the vertical y component. Here we use the cosine to find the vertical y component. So as I've already mentioned on many occasions, the only thing you know for sure is that the cosine gives you the adjacent side. It may or may not give you the x or the y component. You have to figure that out based on the details of the problem. Similarly, you can't assume that the sine is going to give you the vertical component. In this case, the sine ended up giving us the horizontal component. The only thing we know for sure is that the sine gives you the opposite side. Why did we want to figure out these components in the first place? Well, remember that we're basically trying to add these two vectors together. We're trying to add the 6-meter vector and the 4-meter vector to find what the overall displacement is from where we started. Well, now we can kind of combine those. It's kind of common sense now. So initially, we walked 5.6 meters in the positive horizontal direction. 5.6 meters in the positive horizontal direction. And then we walked 1.7 meters in the negative horizontal direction. First we went 5.6 meters in the positive horizontal direction, and then we went 1.7 meters in the negative horizontal direction. So 5.6 minus 1.7 should give us our overall horizontal displacement. 5.6 minus 1.7, that comes out to be 3.9, positive 3.9. So our overall horizontal displacement is positive 3.9. Overall, we've gone positive 3.9. We could label that over here. If we go 5.6 meters to the right and then 1.7 meters to the left, we end up 3.9 meters to the right of where we started. Starting from here, we went 5.6 meters to the right, then we went 1.7 meters back to the left, so we ended up 3.9 meters to the right of where we started. How about vertically? Well, and by the way, notice how important it was to get the right sign on this number. You certainly wouldn't want to do 5.6 plus 1.7. Instead, you have to do 5.6 minus 1.7 because we were walking in two different directions. So hopefully you can see here how important the signs are. How about vertically? Well, first we walked 2.1 meters up, and then we walked another 3.6 meters up. 2.1 meters up. And then another 3.6 meters up. So we just add those together to get that, in total we went 5.7 meters up. 2.1 meters up, and then 3.6 meters up. That gives us 5.7 meters up total. Positive 5.7 meters up. First we went 2.1 meters up, then we went 3.6 meters up. In total we ended up 5.7 meters above where we started. Again, you can see, as I mentioned at the beginning of these vectors, what a clever trick this is. There's no simple way to add the 6 and the 4 because those are not parallel. But we can easily add the two horizontal components because those are parallel. And we can easily add these two vertical, or I should actually say the two horizontal components were antiparallel, but they're still easy to combine. And we can easily combine the two vertical components because those are parallel. So breaking things into components is a very clever trick because the horizontal components will each be parallel to each other and the vertical components will be parallel or anti-parallel, and it's easy to combine those. So now we can see how far we are horizontally and vertically from where we started. Again, this is the payoff from having broken the overall vector into components. Okay, I've erased a lot of the parts now of the original diagram. All that I have left is the overall resultant displacement vector. I've erased the two parts of the path. All we have here is the resultant vector, because now we're ready for our last step. We know that the resultant vector overall has a vertical component of positive 5.7 and a horizontal component of positive 3.9. But now we'd like to find what's the overall magnitude of the overall vector here. How far is the final point actually from the initial point? Well, this is one of the other skills we've learned. We've learned how to take the components and build up the overall vector. How can we take these components and build up the overall vector? Well, remember that when you know two sides, you don't need a trig function to find the third side. You can just use the Pythagorean theorem. The hypotenuse is what we don't know. One of the legs is 5.7. The other leg is 3.9. It doesn't make sense to plug in signs here because these are lengths and magnitudes. We can use our calculator to do 5.7 squared plus 3.9 squared. That's 47.7. Now that's just the hypotenuse squared. Now we got to get the hypotenuse term by itself by getting rid of the square term. Well, the way to get rid of a square is by doing the opposite, taking the square root. Positive square root because we want to end up with a length. Well, if you square something and then take the square root, you go back to the original variable, which is just the hypotenuse here. And we can use our calculator to find the square root of 47.7, which is about 6.9. This came out positive, but I'm not going to indicate the sign because it's just a length. Lengths are always positive. And I'm still not going to indicate the sign even in this picture, because remember that this number refers to the overall vector. Well, remember that overall vectors don't have signs. Because overall vectors are not parallel or anti-parallel to an axis, they don't have signs. So all we can say is that the magnitude of the overall displacement is 6.9. The magnitude of our overall displacement is 6.9. So we know that ultimately we ended up 6.9 meters from where we started. We're 6.9 meters from where we started. Remember that we had two different paths here. We walked for 6 meters in one direction and then 4 meters in another direction. But you certainly can't just add 6 and 4 or subtract 6 and 4. There's no simple way to add the 6 and or subtract the 6 and the 4 to get 6.9. The only good way to attack this was the trick we used of breaking the overall vector into components. And now we've taken the components and we've figured out the overall vector. The overall vector has a magnitude of 6.9. Remember that we're not really done, though, unless we can also indicate this direction over here. We'd also like to indicate this direction. And the way, remember, how do we indicate the direction of an overall vector? By indicating an angle that it's forming. Well, this is the natural angle to try to work out this angle down here. We want to use the components. We could use the hypotenuse here, but conventionally we figured out this angle at this point using the components. Because remember, we figured out the hypotenuse from the components. Let's use the information that we had earlier about the components. Well, this side over here is our adjacent side, and this side is the opposite side. So we want to use the tangent, because we're dealing with the opposite and adjacent sides, TOA. Tangent of theta is opposite over adjacent. The opposite side here had a length of 3.9, and the adjacent side had a length of 5.7. Remember that we don't plug in signs here because these are lengths. You can actually get quite messed up at this point if you try to plug in signs. This tangent approach can give you misleading answers if you try to plug in signs. Since we're working with trig functions, we should just be plugging in magnitudes. Let's do 3.9 divided by 5.7 on our calculators. That's 0.68. 3.9 divided by 5.7 is 0.68. The last thing we have to do is get the theta by itself by removing this tangent function. The way to remove a function is by doing the opposite, and the opposite of a tangent is an inverse tangent. So we have to take the tangent of theta and do the opposite, take the inverse tangent of that. Remember that the -1 indicates an inverse tangent. And then the golden rule of algebra says that that's only legal if we also take the inverse tangent of the right-hand side, which remember is 0.68.